Okay, so at the end of the last video, we talked about how the voltage reading across a battery can be different depending on whether the battery is loaded, meaning there's a resistor connected to it, or unloaded, meaning it's just like a battery out there in the wild. Okay, and so the reason for the difference between those two voltages is what's called internal resistance. Now, up until now, we've basically been ignoring the possibility of internal resistance, but it turns out that all real batteries have what's known as internal resistance, meaning they have natural limits to how rapidly the chemical reactions can maintain the voltage. And so there's some like naturally occurring resistance inside the battery itself. Now, I need to be very clear that even though we draw this, the way we draw this is usually something like this, where we have the what's called the EMF, the electromotive force. We draw it symbolically as though there's a small r, which is internal resistance, and then usually they put a box around it. And so this whole box represents the battery. And so symbolically, it's usually represented as a tiny little resistor inside the battery. I need to be very clear, there is not a tiny little resistor inside batteries. That's not how that works. It's a a symbolic thing. Okay, so when you see that tiny little R, that's the symbol for internal resistance, understand that's just to represent the concept of internal resistance. There's not actually a resistor inside of there. Okay, but there is still a voltage drop inside the battery due to that internal resistance. Now, the power supplied, P supplied from the battery is given by the equation V equals I times V, okay, just a normal PIV equation. But instead of V, we write E for EMF. Okay, so basically inside the battery, you have the actual voltage being supplied, which is E, that's the EMF. You have this internal resistance here, and then the voltage of the entire battery itself. Okay, that is the voltage between the two sides of the battery, aka the terminals of the battery. This is what's called VT for terminal voltage. Okay, and so up until now, we've basically been assuming that um, all of the batteries or all of the cells we've seen so far have no internal resistance, meaning that the terminal voltage is the same as the EMF. Okay, which is not the case, and we'll see that more expressed clearly in the examples we're going to do here in a minute. Okay, but anyway, the power supplied by such a battery is just the current times the EMF of the cell. Okay, now because there is real internal resistance inside the battery, there is some power dissipation inside the battery itself. In other words, there is heat being produced inside the battery. Okay, and this is why you have to be really careful to not create a short circuit with the battery, because if the current has no place to dump that voltage, then it's going to be dissipated inside the battery itself, and that can cause the battery to heat up and possibly explode, which is bad since batteries have acid in them. Okay, the power dissipated inside the battery is given by P equals I squared times little r, where r is the um, internal resistance in ohms, of course. Okay, so make sure you understand the difference between power supplied and power dissipated when referring to a real battery. Okay, so pause there, make sure you understand the difference between that, and let's move on. Okay, that's just a simple calculation. Feel free to look at that. That's very simple calculation involving power dissipation inside a battery. Okay, so just to summarize the concepts we've been talking about so far, we've talked about EMF, okay, electromotive force, which is not actually a force. So EMF is measured in volts. Okay, it was just given the name electromotive force but before we understood what was happening. That's the total energy per unit charge supplied by the battery around a circuit. Okay, that in other words, the EMF is basically the voltage supplied by the battery without a resistor attached or without internal resistance. Okay, so every single problem we've done up until now, when we talk about like the cell has this many volts, really we've been talking about the EMF and assuming there is no internal resistance. Okay, what we call the terminal voltage is the actual measured voltage across a battery when it is connected to a circuit. Okay, so in other words, the terminal voltage, I will write VT. That would be the EMF minus the voltage loss inside the battery. Okay, and voltage drop is given by V equals I times R. So that would be I times little r, where little r is the internal resistance. Now, in the last video, we talked about the difference between loaded and unloaded voltage across a battery. Okay, so here we can see where that comes from. Unloaded voltage across the battery is just the EMF. Okay, when you attach it to a load, in other words, when there is current going through the battery, there is a voltage drop inside the battery due to the internal resistance, which is where you get the terminal voltage from. Okay, so I think at the end of the last video, the EMF was like 1.6 volts, and then when we hooked it up to a circuit, the voltage we measured across the battery itself, the terminal voltage, I think went down to 1.5 volts, meaning that inside the battery there was a voltage drop of 0.1 volts due to this term right here, due to the internal resistance. Okay, so make sure you understand the difference between EMF, which is the total like voltage that the cell is capable of supplying, and the terminal voltage, which is what you would get if you were to just like take out your voltmeter and put it across the battery. Okay, those two numbers are the same if the battery is not hooked up to something, but if a current is coming out of the battery, then they're not the same. All right, so let's take a look at an example problem. Okay, so here we can see how it's drawn schematically. Okay, this battery is drawn with the internal resistance represented by a resistor symbol. Again, there is not a resistor inside a battery. Okay, this is just to denote the fact that there is resistance inside the battery, but there's not actually like a tiny little resistor, if that makes sense. That's just how it's drawn in the circuit diagram. So the question says, in the circuit shown to the left, the EMF of the battery is 10 volts. Okay, meaning E is 10 volts, and the current flowing through the circuit is 0.85 amps. Okay, the value of the resistor R is 10 ohms. Okay, so we know this one out here is 10 ohms. We know the current flowing is 0.85 amperes. The first thing we're asked to do is find the internal resistance of this battery. Now, in any given situation where you don't immediately know where to start, a safe thing to always go to is Kirchhoff's circuit laws. Okay, so my first instinct is to do the loop rule and see if that tells me anything. Okay, so I'm going to draw a loop. I always like to start at the negative side of the battery and go in the direction of the current. And so if you apply the loop rule, I'm adding up the voltages. I go up E, that is up 10 volts. I experience a voltage drop across the internal resistance, which would be given by V equals I times R. So that's going to be minus I times R, which I don't know what little r is. And then I keep going. Here again, I have a voltage drop given by V equals I times R. Okay, so that's minus I. And big R is given in the problem as 10. And I keep on going. I get back to B. I set this equal to 0. And lo and behold, I have an equation given to me by the loop rule that lets me solve for little r. Now, how did I know to do that? Well, like I said, if you ever get stuck on a problem, just start writing down equations for what you know. Okay, in this case, I just hope for the best. I just went straight to the loop rule and fortunately found out how to get little r. Okay, so if you rearrange this correctly, let's see. So 10 minus 8.5 is 1.5. Okay, and then we need to divide by 0.85. And so we get little r is 1.76 ohms. Okay, so that's the first question. Now the second question says determine the terminal voltage of this battery. And again, terminal voltage is the voltage across the terminals of the battery. In other words, the voltage between B and A. Okay, so in other words, if we were to stick a voltmeter in here, okay, across the sides of the battery, this V is the terminal voltage. Okay, now how do we find the terminal voltage? Well, if you imagine just doing um, the loop here, we should be able to see that the terminal voltage is just going to be 10 volts minus however many volts we lose here. Okay, and I can tell you how much that's going to be because from the calculation I did before, I had 10 volts. I lost 8.5 across the big resistor, which basically means I have uh, a voltage drop of 1.5 inside the battery. Okay, so I know that the terminal voltage is going to be 8.5 volts. I can also think of that as, you know, if you ignore the internal resistance of the battery, if you just treat it as like a voltage source, if I know that there's only one thing in the outside circuit, and that's the resistor big R, and I know the voltage there is 8.5 volts, I know that that 8.5 volts has to come from the battery, and so that would be the terminal voltage. Okay, and the last question, calculate the power supplied by the battery. Okay, that would be I times V, or in this case, I times E, which would be 0.85 times E, which is 10. And so that is going to be 8.5 watts. Okay, so the battery is supplying 8.5 watts. Pause there if you need to look at that some more. Okay, so I think most of this we've talked about before. Okay, this is just a very similar type of example to the one that we just did. Okay, so I'm going to go past that. Okay, so I want to take a look at an actual IB question before we move on past internal resistance. Okay, so experimentally speaking, you can determine EMF and internal resistance by a certain type of setup. Okay, and the diagram for the setup looks something like this. Basically, the way that you would actually find the internal resistance for a battery, and I guess you could do this as an IA topic, it might be too easy. Uh, but if you want to use this as a basis for an IA topic, you could. Um, but basically what you do is you take a voltage source, okay, like a battery, and notice in the schematic, in the circuit diagram, you have a voltmeter across the battery measuring the terminal voltage. You have an ammeter measuring the current. Okay, this symbol down here, the box with an arrow going through it, that is the symbol for a variable resistor, which is basically a resistor where you can change the value of the resistance. Okay, and so the idea of how you would find the terminal voltage is you would basically collect data. Okay, you would measure the terminal voltage and you would measure the current, and you would change those things by changing this. Okay, so when you change this resistance right here, because it's a variable resistor, that's what it does. When you change the value of big R, you change the current. Okay, and you also change the terminal voltage. And basically what you're going to get is you're going to get values that look something like this if you make enough measurements. Okay, now because the terminal voltage by definition is equal to the EMF minus the voltage loss inside the battery, which is I times little r, if you make a graph where you have the terminal voltage on the y-axis and the current on the x-axis, imagine if this is your y and this is your x, this is actually in the form of an equation of a line, okay, where E would represent your constant value, that would be your y-intercept. Actually, I guess I should write that as B. and little r would be the slope of your line. Okay, and so by collecting enough data points and figuring out what that line looks like, by measuring the y-intercept and measuring the slope of that line, you can experimentally determine the EMF and the internal resistance. Okay, and so I want to take a look at an IB question where they do that before we move on. Okay, so pause it there, make sure you add that to your notes, and then we'll take a look at that problem. Okay, so the lemon question. This is actually from an IB exam question a couple of years back. So this question says, and I'll put this on Canvas as well. This question says, a lemon can be used to make an electric cell by pushing a copper rod and a zinc rod into the lemon. A student constructs a lemon cell and connects it in an electric circuit with a variable resistor. The student measures the potential difference V across the lemon and the current I in the lemon. Question 1 says, draw a circuit diagram of the experimental arrangement that will enable the student to collect the data for the graph. Okay, and so this is just a matter of understanding what I just showed you. How would you have a circuit diagram set up to collect this information? Okay, so let's pretend that this is the limit. Okay, we want, number one, a variable resistor. Okay, and so the symbol for that would just be a rectangle with an arrow. Remember, you can always look at the data booklet if you don't remember the notation for something. We also want an ammeter that is capable of measuring the current through the lemon. And so this is our basic setup. And then we also want to measure V across the lemon, meaning we have to have a voltmeter in parallel with the lemon itself. Okay, remember, ammeters have to be in series with whatever you're trying to measure, and the voltmeter needs to be in parallel with whatever you're trying to measure. Okay, so something like this. Okay, so pause there if you need to look at that some more, and then I'm going to erase this. Okay, the potential difference V across the lemon is given by V equals E minus IR, where E is the EMF of the lemon cell and R is the internal resistance of the lemon cell. Which you should already know that equation anyway, but they give it to you. The graph shows how V varies with I. And notice they give you some data points. Using the graph, estimate the EMF of the lemon cell. Now, if you understand the connections that we just made a minute ago, then you should recognize that because of the formation of this equation, the EMF can be found by looking at the y-intercept of such a graph. And so what we want to do is we want to try to sketch a line of best fit. This is not going to be perfect because we all know I can't draw. But the y-intercept here is very roughly going to be around 1.6 volts. That's why it says using the graph, estimate the EMF of the cell. Anytime that says using the graph, by the way, you should explain like how you use the graph and make it clear how you're using the graph. Okay, so for this question, from the graph, the y-intercept is about 1.6 volts. So the EMF is about 1.6 volts. Okay, something like that. Again, anytime you have a question telling you to use the graph, you need to make it clear that you did in fact use the graph. Don't just like start writing down random numbers without explaining how exactly you're using the graph to get that answer. Okay, so that's probably a point right there. And then the next question says, determine the internal resistance of the lemon cell. Okay, now I said before that the internal resistance in the equation would be representative of the slope of this line, but it doesn't ask us to estimate anything. And so rather than try to find the slope of this like weird line that I can't really draw, what I'm going to do is I'm going to use my EMF value and I'm going to pick one of the data points and I'm going to plug into the equation and use that to answer the question. Okay, so let's see what a good data point would be. I guess I'm going to use this one up here. So this data point, let's say 1, 2, 3, 4, 5. So there's 5 spaces between 1.4 and 1.6. So each of these is 0.04. Okay, so that would be 1.44, 1.48, 1.52. Okay, so that would be about 1.52 volts. And so if the terminal voltage is about 1.52 volts, and I know the EMF is about 1.6 volts, and I know the I at that point just by looking at the graph, I will need to estimate a little bit because this is not drawn perfectly, and it's kind of hard to see because the boxes are so small. It appears to me each of the boxes is zero point 0.1 milliamps, and so that would be about 0.25 milliamps right there, which of course you need to make sure that you convert 0.25 times 10 to the negative 3 amperes, and then you could just plug those values into this equation, rearrange and solve for little r. Okay, which I'm not going to do just in the interest of time. Okay, but that's how you would approach that type of problem. Okay, and I will try to post a lemon question on Canvas so you can take a look at that and try it on your own. All right, so the last thing I want to talk about in this video are sensor circuits. Okay, now we've talked about these two types of components before, thermistors and LDRs. These are special type of resistors whose resistance depends either on temperature or on light intensity. Okay, for a thermistor, generally speaking, as the temperature of the thermistor increases, the resistance of the thermistor decreases. And it's the same thing for an LDR, except with light intensity rather than temperature. Okay, now these types of components can be used to create what I like to call sensor circuits. Or basically, for example, if a change in temperature is detected, then the circuit has a way to figure that out and make something happen. For instance, if you set your AC to 72, your thermostat has to have a way of detecting if the temperature goes below 32, I should turn on the air. Okay, and so that type of circuit probably has a thermistor in it to do that detection. Okay, or in LDR, you sometimes see those in like nightlight circuits, or circuits where if you've ever gone into like a dark room, when you open the door, when the system detects like the light intensity goes up, it knows to turn the lights on. Okay, and so those types of circuits there can be used to create sensory type of circuits. Okay, now the basis for a sensor circuit is what's called a potential divider or a voltage divider. Okay, and so that's what we're going to talk about now. Okay, and we'll get into more depth in the next video, which is going to be the last video in this unit. Okay, so let's say we have a battery that's a 6-volt battery, and we have a light bulb that can only use 3 volts. How can we get 3 volts from a 6-volt battery? And no, you can't just cut the 6-volt battery in half. That's not possible. Okay, so we can use what's called a voltage divider circuit or a potential divider, and that is a type of circuit whose job is to divide the potential. Okay, so a potential divider is a circuit made of 2 or more series resistors, and they don't have to be resistors. They could also be LDRs, they could be thermistors, they could be variable resistors that allows us to tap off any voltage we want that is less than the battery voltage. Okay, so if we have a 6-volt battery, if I only want 2 volts for my light bulb, I can do that with a voltage divider. If I want 3 volts, I can do that with a voltage divider. Okay, and so just to name some things, the input voltage is the EMF of the battery. I guess technically speaking, it would be the terminal voltage of the battery, since you have to account for uh, internal resistance, like we just talked about. Although I will say it's not super common to see problems with voltage divider circuits also having internal resistance, but I guess you could. So even though this says the EMF of the battery, really it's terminal voltage. And then if you have no internal resistance, then EMF and terminal voltage are the same, like we've been talking about. The output voltage is normally the voltage drop across the second resistor. It does not have to be. There's nothing special about that. That's just normally how it is. And so basically you just have you have a battery, you have two resistors in series, and then in parallel across one of the two resistors, in this case R2, you have what's called V out, which is the output voltage. Okay, now I don't like the way these pictures work, so let me draw this for you in a different way. Okay, so here I'm just going to draw this as a cell and ignore internal resistance. Okay, so the idea is you have this is Vn. This is, wow, what am I doing? Okay, so the EMF of the cell, let's call that Vn. You have two resistors, R1 and R2, R1 and R2. This is the EMF. Okay, so the voltage across the cell is what we call Vn. And then V out is typically in parallel to one of these two resistors. Okay, so in this case, this is V out. And by choosing the values of R1 and R2 carefully, we can make V out be whatever we want. Okay, so the last thing I'm going to do in this video is I'm going to derive what's called the voltage divider equation. It is not given to you in the data booklet, and so it would be helpful if you understood how to do this derivation on your own. And then we'll use it to solve sensor type of problems in the last video. Okay, so here's basically how this works. Okay, so we have two resistors in series right here. Okay, so V out is equal to the voltage across, in this case, the voltage across R2. Okay, that's just a given. It doesn't have to be that way. We can also make V out R1. It just kind of depends on what type of circuit you need to make, and a lot of the time they'll give you the diagram and they'll tell you which one is V out. Okay, but let's just say the voltage across R2 is V out, and we want to find an expression for V out. Well, I know that the current, or the voltage across R2 would be the current going through R2 times R2, because I know V equals I times R. I also know that I've got basically two resistors in series, and so if you think of the equivalent resistance in the circuit as R1 plus R2, I can find out what I is by just saying, okay, V equals I times R. If this is my Vn, that's equal to my I total times Req, which would be I total times R1 plus R2. And I total, which I'm just going to call I, because there's only one current in this whole thing anyway, okay, is equal to Vn divided by R1 plus R2. And so what I now have is I have derived an expression for I, which I can now go back in up here and plug in up there. And if I put all that together and make that substitution, I find that V out is equal to I, which is Vn divided by R1 plus R2 times R2. Okay, and so this is what's called the voltage divider equation, or the potential divider equation. And it's not given to you in the data booklet. It would be a good one to know, or even if you don't know, be able to derive it. It's definitely not an equation I have like just sticking in my head somewhere. I always would have to derive this from scratch, but it's not hard to do this derivation as long as you understand the concepts involved. Okay, and so basically what this means is if I know Vn and I know that V out has to be this number, I can choose what R1 and R2 have to be in order to make the circuit do what I want to be done. Okay, so for example, in the problem we just saw, if I want V out to be 3 volts and I only have a 6-volt battery, okay, that gives me 6 times R2 divided by R1 plus R2. If I know, well, let me just kind of rearrange this actually. if I multiply both sides by R1 plus R2, then that would give me 3 R1 plus 3 R2 is equal to 6 R2, and that gives me 3 R1 is equal to, let's see, if I subtract 3 R2 from both sides, I get 3 R2. In other, in other words, R1 equals R2. In other words, if I want to take 6 volts and split it into 3 volts, all I have to do is make sure R1 and R2 are equal to each other. Okay, and it doesn't matter what the actual values are, they just have to be equal to each other. Okay, and so that gives me a way to take any input voltage I want and split it to give me what I need for my devices. Okay, so in this example, I need 3 volts because my light bulb only works with 3 volts, but I only had a 6-volt battery to work with. Okay, so all I do is I build a simple circuit and I make R1 and R2, whatever I have lying around, as long as they're both the same resistance, then I can get my 3 volts. Okay, so that's just a really basic example with a voltage divider. In the next video, we will finish this unit up and talk about some more complicated voltage divider circuits where you have thermistors or LDRs or stuff like that. Okay, as always, please let me know if you have any questions, and I'll see you guys in the next video.